As of late 2024, the National Health Service in England faced an operational backlog of approximately 7.8 million patients. Look closely at these emergency department metrics. This bottleneck is a symptom of a physical deficit. The system lacks the diagnostic and surgical capacity to process current demand. Built in 1948, the original NHS architecture was not designed to handle today's pressures. An aging population with complex comorbidities, compounded by the tidal wave of deferred care from the COVID-19 pandemic, has pushed the existing estate past its physical limits. The proposed solution is to bypass multi-year construction entirely. Health trusts can rapidly deploy standardized, modular diagnostic and treatment units directly onto hospital grounds. To understand how this works in practice, we will examine a case study, expanding a district general hospital with a new modular unit, capped at a firm budget of £5 million, with a rigid completion deadline of 23 weeks. Delivering public infrastructure at that velocity leaves no margin for error. You cannot manage a 23-week timeline with passive reporting. Hitting this deadline requires an airtight, mathematically integrated project control baseline. Every day of work and every pound spent must be tracked, linked, and forecasted. We will map the procurement strategy, translate the physical scope into a rigid cost structure, sequence the timeline, and deploy prospective delay analysis to protect the final delivery date. Applying rigorous data-driven engineering to capital projects establishes a transparent, repeatable mechanism for transforming public funds into functional clinical capacity on a predictable 23-week cycle. Before any physical planning begins, the project must survive the first trap of public construction. Traditional competitive tendering, the design-build-build model, routinely consumes 6 to 12 months in bureaucratic approvals. To hit our 23-week timeline, we use a framework agreement, specifically utilizing established routes like the NHS Procure 22 and Procure 23 programs. A framework establishes a pre-vetted panel of contractors. Because these suppliers have already passed exhaustive financial and technical assessments, the NHS Trust can issue call-off contracts without triggering a full open tender exercise. Traditional public procurement frequently sees final outturn costs exceed contract sums by 10 to 30%. NHS frameworks, by utilizing pre-negotiated rates, achieve an average cost certainty of 97% at contract award. These panels also enforce specific supply chain requirements. Every approved contractor is pre-screened for compliance with highly specialized NHS infection prevention and control standards. The NHS Nightingale hospitals, some of which were functional in under 2 weeks, demonstrated the immense velocity that is achievable when procurement complexity is minimized. Selecting a framework agreement is the critical administrative prerequisite. It allows the 23-week timeline to exist, rather than being consumed by procurement lead times. With the contractor secured, we define exactly what they are building. The Project Management Institute dictates the 100% rule, which mandates that absolutely every piece of project scope must be mathematically accounted for. This diagram shows the work breakdown structure, or WBS. We deconstruct our modular hospital into 13 discrete, manageable work packages. These packages are grouped into 6 distinct categories, starting with site preparation and moving through design, procurement, construction, commissioning, and final project management. We map the £5 million budget onto this architecture, creating the cost breakdown structure. Every node now carries a precise financial weight. The highest financial density is in construction and installation. Physical assembly, weatherproofing, and substructure account for 42.1% of the total budget. To adhere to HM Treasury Green Book appraisal requirements, we apply a 10% risk contingency across all of these work packages to absorb localized cost shocks. Fusing the scope to the cost at this granular level eliminates ambiguity. It provides the structural backbone required to actively manage the project's time. To create a dynamic schedule, we sequence our 13 packages into an activity-on-node network, mapping linear dependencies. We calculate the total float for each task, subtracting early finish from late finish. This reveals how long a task can be delayed without impacting the final delivery. Tasks with zero total float form the critical path. This sequence of dependent activities determines the minimum duration of the project. For our modular unit, the critical path routes through site survey, demolition, groundworks, module order, erection, and handover. Activities like architectural design are near critical, possessing only 1 week of float. Slipping by 8 days delays final handover. The network's highest vulnerability occurs at week 9, where foundation works and off-site modular manufacturing dependencies intersect. Because the critical path has zero flexibility, any delay along this red line translates directly into postponed procedures for patients on the waiting list. A static project baseline is largely theoretical. The moment ground is broken and contractors arrive, reality deviates from the initial plan. To prevent deviations from becoming failures, managers use Earned Value Management, or EVM. This is a predictive framework that continuously measures physical work accomplished against the integrated baseline. This chart plots performance over 23 weeks, tracking 3 core metrics: planned value, earned value, and actual cost. Notice the first 5 weeks. Actual cost temporarily spikes above planned value. This is common in NHS construction, driven by mobilization and site preliminary costs. The critical metric here is the Cost Performance Index. If the index drops below 0.90, it signals a cost overrun that requires the project manager to file an exception report under the Prince2 governance framework. EVM transforms financial tracking from a post-project autopsy into a real-time, predictive radar system for capital control. But what happens when an unavoidable event, such as discovering poor ground conditions, physically stalls the critical path? A frequent industry mistake is to wait until the project finishes and then retrospectively argue over which party is responsible for the delay. We avoid this by using time impact analysis, a methodology grounded in the SCL protocol. TIA evaluates delays prospectively, at the exact moment they occur. It works by quantifying the delay event as a discrete block of time and logic, known as a fragment network, or fragnet. Look at the baseline schedule. We take the delay fragment and insert it directly into the timeline at week 5. The math proves the consequence instantly. The insertion ripples through the remaining dependencies, pushing our predicted completion date back to week 24. This clarity gives the NHS Trust the data needed to test targeted acceleration options, such as increasing labor in week 19 to recover the lost time before it compounds. Frameworks bypass bureaucracy. Breakdown structures lock the scope. Network diagrams sequence the time, and EVM and time impact analysis defend the reality of the 23-week plan. This level of structural discipline provides a reliable framework for the NHS to deliver the physical architecture needed to address a 7.8 million patient waiting list.